briefly, so it is our great pleasure and honor to welcome Professor Kamran Behnia for the online BOS colloquium series, which we have on quantum materials and devices. Professor Behnia needs no introduction to the community of condensed matter physicists and material scientists, but I'll just briefly introduce him. So he is a world-renowned experimental condensed matter physicist from ESPCI-Paris. He received his PhD from Grenoble in 1990, and he worked on thermal transport on heavy fermionic systems in his PhD days. And then several years he spent in CNRS after his PhD, where he worked on some organic and cuprate superconductors. He then joined this present institute where he is working now in 2000, exactly at 2000, and he has been working on many interesting condensed matter problems. For example, unconventional superconductors. As we all know, he has been working on bismuth for since many years, and he is one of the experts on thermal transport studies. So he could do very accurate experiments on thermal transport, for example, his thermal Hall effects or Nernst effects. And students might know him from his very famous book, which is on the thermoelectricity from Oxford University Press. He became a fellow of American Physical Society in 2012, and he has served as board of reviewing editors of journal Science, and he was also divisional associate editor of Physical Review Letters. So I think we, without doing further ado, we should listen from Professor Behnia himself.
Thank you very much, Nitish. Thank you for this invitation. I am honored to give this presentation in this institute. And the subject of my talk is very general. I hope that you can, it's not very technical. And let me present my collaborators. Benoit Fouquet is my younger permanent researcher. Actually, we work very closely together during the last few years. Several people who are, have been active in presenting this research are now in different places. Alexandre Jaby is now in Barcelona. Shaolin is back in China. Clément Collignon is in MIT. And Willem Rochaud is now in Geneva. But they all participated in the experimental results I'm going to present. Now, what I'm going to talk about is a very old subject. And actually, I think most of you, all of you know that you have heard that Fermi liquids have T-square electrical resistivity. And this is considered to be conventional compared to something which is strange, like in high temperature superconductors, people talk about strange metallicity because you don't see this T-square resistivity. What I'm going to talk about is that this T-square electrical resistivity, first of all, is not as well understood as you often take it for granted, that it has a thermal counterpart. It was said that I am an expert in thermal transport, I'm interested in thermal transport, and this is why I began to think a lot about this subject. And I'm going to present some results which are not mine, actually. They're obtained on helium-3 decades ago. And it's very interesting because for us physicists of metal, this original Fermi liquid can be a lesson. And then I will come, I hope, to present an idea about how to understand the emergence of T-linear resistivity in cuprates. I'm not going to, to give a solution to this puzzle, but I'm going to tell you how the problem of strange metallicity becomes less mysterious if you begin by this T-square resistivity. So here is the starting point. The theory of Fermi liquid tells you that if you measure the electrical resistivity of a simple metal, you expect to have a first term, which is the residual resistivity. It depends how clean your sample is, so scattering by impurities. And there's a second term, which is electron-electron scattering, which gives you T-square. Now, you may know also that if you want to look at this T-square resistivity in copper or in gold or in alkali metals, it's very hard to see it. And this is because you have strong electron-phonon scattering. On the other hand, if you want to see it in a correlated metal, like a heavy fermion system, or a dilute metal, like bismuth or graphite, actually it is easy to be observed. It is much stronger than the electron-phonon term. So here I am showing you 4 plots obtained by different people, not at all our group, during the last decades. You can see here is the result for bismuth, a beautiful work by Hartmann in 1969. Resistivity as a function of t squared, it's almost a straight line. And the numbers, you can see it is micron centimeter. Here is t squared, so you can see that you have t squared behavior. The slope maybe is a little changing. The same is true for graphite, obtained by Uer and his collaborator. You can see that the scale where t squared behavior can be seen is much more limited. It stops at 30, but you have a clearly t squared behavior. So these two are dilute metals. I can also show 2 strongly correlated systems like UPT3, strontium luteinate. And this now, so it is true that in many metals you can see easily a t squared behavior. Where does it come from? So let me begin by a bit of history. So the person who proposed this, you may suspect, was Landau with Pomeranchuk. Actually, so this is his first paper on this subject. It is in the list of his scientific papers is here. It was not written in English. It was written in Russian and in German, published in these years. And this paper, so this is the English translation. He proposed this idea that, yes, resistivity should have a t square and a t5 term. T square term comes from the fact that electrons collide with each other. Almost simultaneously, in England, there was this paper by Bubber, where he also proposed that electron-electron scattering should give rise to a t square term. Note that at that time, actually, t square resistivity was rarely observed. So this is really a kind of theoretical prediction, which was confirmed afterwards by experiments. Now, there is a problem. If you think a minute about this, what is this macroscopic origin of this? It is very easy to grasp the underlying argument. You have 2 electrons which collide with each other, and you apply the Pauli exclusion principle twice. The first electron and the second electron. So the phase space for such a collision is going to grow proportional to kBt divided by EF squared. Up to here, everything is fine. But think about it. If 2 electrons collide to each other and momentum is conserved, why should the momentum decay? When you are measuring resistivity, we are assuming that we are looking at the way the flow of momentum by charge carriers is impeded by scattering effects. If electrons lose their momentum to phonons or impurities, that's fine. But if one electron gives its momentum to another electron, why should it matter? So, of course, people knew this, and they had 2 different ideas. One idea, which was explicitly formulated by Bubber, is that if you have 2 kind of electrons, of course, you can have momentum exchange between these 2 reservoirs of electrons. Imagine now that one group of electrons is more solidly, more strongly coupled to the thermal bath. So in that case, you have these 2 reservoirs which are exchanging momentum. This exchange of momentum between these 2 groups of electrons will create a kind of bottleneck. Even if the ultimate loss of momentum is here, since this canal is much wider than this one, you are going to see t squared in this way. So it's very indirect way, but why not? So that was what he proposed, in particular in the case of palladium. The other possibility, which is not explicitly mentioned, but most probably this is what Landau and Pomeranchuk had in mind, was an Umklapp scattering. So Umklapp scattering is when you see the colliding electrons have wave vectors such as the sum of the final two wave vectors minus the sum of initial wave vectors is equal to a vector of the reciprocal lattice. This can only happen if your Fermi surface is big enough. You see, if this is your Fermi surface and this is your Brillouin zone, when the Fermi surface is a sizable fraction of your Brillouin zone, you can easily imagine a process like this one, where you have the first electron from initial to final, the second electron from initial to final, and you see that now you have a huge difference, which is of the order of magnitude of the, which is equal actually to the size of the Brillouin zone. So for this to happen, you need a Fermi surface sufficiently large. If the Fermi surface is too small, you cannot have this. Okay. Now, my story begins with strontium titanite. So strontium titanite, I'm not going to talk about it. It's a perovskite. It is interesting for many different reasons. It is superconducting. It has been studied for water splitting. It's a quantum paraelectric. It squeezes second sound, displays flexoelectricity. It has attracted a lot of attention since the discovery of interface superconductivity and others. So what we did in 2013 was to do some thermiology. And it was, I'm not going to go to the details. We measured actually the Nernst effect, and we saw that you see easily quantum oscillations in the dilute limit. And what was interesting is that when you go to very low densities, 5.5 1017 centimeter minus 3, you have just a single frequency. You can see it here. And actually, the Fermi surface is very small. So here is in units of the reciprocal lattice, and it's basically a small squeezed ellipsoid, as it was predicted by band structure calculations. Now, for the sake of this talk, what is interesting is that you can see clearly T-square behavior. You can actually look at how this T-square behavior evolves when the system is extremely dilute, 4.1 1017. This is equivalent to having 1 electron for 100,000 atoms. And then you increase the carrier density by 2 orders of magnitude. And what you see is that you have a T-square behavior. The slope becomes smaller and smaller as you go to higher and higher carrier densities. Please compare in these panels the vertical axis units. Here is 30, 10, 4. On the other hand, the horizontal axis also changes. It goes to higher temperatures. So as you are going to increase your carrier density, you decrease the amplitude of this A. On the other hand, you increase also the window of validity of this T-square behavior. And if you plot now A as a function of n, first of all, our data joins what was obtained by other groups. This is Tokura's group, obtained in 1990s. This is Vandermarel's group. These symbols, our data are here for both reduced strontium titanite and niobium replaced strontium titanite. And here is the interesting thing. In this part, the Fermi surface is single component, and it is very small. And the T-square behavior survives. So here is the puzzle. Neither the Buber mechanism nor the Umklapp mechanism can explain the persistence of T-square resistivity in this context. Somehow electrons, when they collide with each other, the thermal bath takes a kind of tax on momentum exchange. You cannot avoid losing some momentum to the thermal bath when you are exchanging electrons, momentum with other electrons. Okay, actually, this paper was published in 2015, and it stimulated theoretical work. And actually, people like Dmitry Maslov came with explanation that actually maybe in the case of STO, what you're seeing is not electron-electron scattering, but some very exotic kind of electron-phonon scattering. The thing is that, of course, he's partially right. The strontium titanite conductivity is a complicated business. But what I wanted to show here is that afterwards, Xiaolin, who went back to Hangzhou, he also discovered that T-square resistivity exists in another system, which has a very different phonon spectrum, bismuth to oxygen to selenium. This is the crystal structure, and again, the Fermi surface is very small, single component. And actually, if you can look at this behavior, you see the result is not very similar, very different from what we saw in STO. And this brings us back. We should find a way to understand T-square resistivity. So here's the beginning of the story I want to tell you. And I think even now at 2022, we are not yet in presence of a good understanding of the microscopic mechanism which creates this T-square resistivity. So let me now begin with another point of mystery. In 1968, Rice plotted this figure. He took the T-square resistivity of several elements. Here you see osmium, rhenium, cobalt, iron, platinum, nickel, palladium as a function of gamma square. And he found that this A, the prefactor of T-square resistivity, scales with the square of gamma, which is the linear T-linear electronic specific heat. 18 years after, Kadowaki and Woods made this plot very famous because they plotted this kind of plot, A have a gamma in a log-log plot. This is a linear plot. Here you have a log-log plot. And he found that actually the same correlation with a different prefactor is valid for heavy fermion systems. This was a very, so I am going to call it Kadowaki-Woods scaling, even if Rice was the first, because this is now what has been popular in the heavy fermion community among which I grew up, actually. So the postulating is that actually this A term is proportional to gamma square in different materials. Gamma is the T-linear specific heat. Now, one thing you should have in mind is that, and it was only understood very recently, is that this is valid for dense metals. You see, the reason this scaling works roughly is that your specific heat, basically, for a Fermi liquid, you can use your T-linear specific in this way. So it is proportional to Boltzmann constant square and the ratio of carrier density to the Fermi energy. If I write now the A term, I can also write it, this is a resistivity. This is the inverse of the quantum of conductance, if you wish. You have this term which represents size of the phase space, and then in 3 dimensions, you will have a kind of phenomenological length scale that I will call L quad. Now, if n is equal to 1, then you would expect these two guys to scale with each other because of the fact that the Fermi energy is the energy scale in both. In one case, it is the square of the Fermi energy. In the other case, it's just the Fermi energy. But if you have whatever n, A should be proportional to square of EF square, but gamma will cease to be just the inverse of 1 over EF. And this reflection that I'm making makes sense if you go back to Rice's data. In his data with metallic elements, dilute metals are absent. If I put bismuth, graphite, and antimony, they are here, very far from what he plotted. If I put aluminum or tungsten, they will join his line. On the other hand, these are okay. So I wrote a review paper about this, and you can gather. So this information was already known in 1968. There was no internet, and probably people were not as easily capable of gathering information as we are today. But anyhow, these metals were missing. Of course, people can say, okay, maybe it was not electron scattering. But if now I put the same data on EF, I see that actually the extended Rice or Kadawaki scaling works. There is a point. If you put bismuth, which has a rather large T-square resistivity, this is basically because its Fermi energy is very small. If you measure its gamma, it's very small, but the gamma is small because the carrier density is very small. So this extended Kadawaki-Woods scaling works rather well. These were elements, but actually, as we found out, you can actually put almost anything measured on this scale, in the sense that here are a lot of dilute systems. You have, of course, heavy fermium systems, but this is our data on strontium titanite. These are the data on transition metals. And basically, this is over 5 orders of magnitude for Fermi energy and 8 orders of magnitude for the resistivity prefactor. Of course, there is not a single number, but it looks like this slope is defining a kind of margin between what is the expected T-square resistivity of a metal given its Fermi energy. And now you see, actually we have a second puzzle. Not only we don't understand why the T-square resistivity persists in absence of Umklapp scattering, the second question is, how come that it is universally linked to the Fermi energy? If you have different kinds of mechanisms, which depends on the size of your Fermi surface or the presence of 1 or 2 reservoirs, how come that actually, in most cases, you can predict the magnitude of your T-square resistivity just knowing the size of your Fermi energy? So here, I switch gears, and I would like to talk about thermal transport. Let me begin again with something very old, and this is the law of Widman and Franz. The Widman-Franz law, discovered in the middle of the 19th century, persisted across the 20th century. Here is a experimental Lorentz numbers listed by Kittel. You see that what these two German gentlemen found in 1853 is still true today, in the sense that if you measure resistivity, electrical resistivity of a metal at room temperature, and you measure its thermal conductivity at room temperature, and you look at the ratio of electrical and thermal conductivities divided by temperature, you find something which is almost the same in different materials. And the modern formulation is that if you take this Lorentz number, the ratio of these two conductivities divided by temperature, it should match the Sommerfeld ratio, which is this ratio of Boltzmann constant and the charge of electron times P2 over T. This is something that is now well enshrined in the quantum theory of solids. This is because electrons carry both charge and entropy, and you can ask several questions why it is a power of 2. This is because charge and entropy quanta are present both for the force and the flux. Why it is a pi 2 over T? It is just a consequence of Sommerfeld expansion. Now, thermal conductivity measurements are harder than electrical conductivity measurements, and we have less data. But let me just show you two kind of data. People have measured thermal conductivity and compared the thermal resistivity with electrical resistivity. And what people find is that if you look at this thermal resistivity, which I call it WT because you see thermal conductivity per se should go to 0 at 0 temperature because of the third law of thermodynamics. What's happening is that it can have a linear term. So if you take this thermal conductivity divided by temperature and inverse it, you have a quantity which I'm going to call thermal resistivity. It is actually thermal resistivity times temperature, which can have a residual term and a slope. And the slope, very much like electrical resistivity, is T squared. Now, if you compare these two numbers, what is found is that at zero temperature, you recover the Widman-Franz law, in the sense that the residual electrical resistivity and the residual thermal resistivity are correlated with each other. But if you look at it, the slope is larger. So you have a deviation from the Widman-Franz law at finite temperature. And this is known and has been understood as the fact that, you see, you have horizontal processes. If you are measuring thermal transport, you create a temperature gradient across your Fermi sea. So in that case, you are interested in the way heat is carried by this difference between occupied and unoccupied state. So in addition to these horizontal processes, you have also vertical processes. In the case of electrical conduction, where the charge is carried by particles which are focused at the Fermi surface, you only have these horizontal processes. So this small angle scattering, which occurs when a carrier of heat is scattered in a way that it just drops across the Fermi level, is not operative here. For having an electrical resistivity, you should think of an event which actually brings an electron from this side of the Fermi sea to this side of the Fermi sea. And because of this, a small angle scattering is less efficient for the charge current, and there is a pondering factor for momentum current, which is absent for energy current. So this has been the traditional way of understanding why the two slopes are different. Okay, so I stated the state of understanding here, and now, since we are talking thermal transport, we can go and consider the situation in a charge neutral Fermi liquid. Actually, I'm talking about the original Fermi liquid, the one who inspired Landau to formulate his Fermi liquid theory. And this is helium-3. Helium-3, as you know, remains a liquid down to zero temperature. It becomes a superfluid below 2.8, but there is a Fermi liquid region above the superfluid transition and below almost 1K. And of course, the collisions is also proportional to T-2, the same Pauli exclusion principle, which gave rise to a T-2 behavior of the T-square resistivity of the Fermi liquid, is actually here also present without complications due to the presence of disorder or a lattice. Now, thermal conductivity of normal liquid helium-3 has been studied in detail, and what experimentalists found in agreement with theory is that thermal conductivity is proportional to the inverse of temperature. Now, for some reason, which escapes me, nobody had paid attention that actually this kappa proportional to T-1 is strictly equivalent to WT proportional to T squared, which is what us metal physicists are talking about. If I plot, so here is the data from Greywall, the paper I just mentioned. If you look at, so this is the phase diagram of helium-3. So this is temperature, this is pressure. You have a superfluid state with two different phases, A and B. You have a normal liquid here. What Greywall did was to measure thermal conductivity in this region. And if I translate his data in the language of metal physicists, you will see that you have a WT term with no residual term because no impurities here, which has a T2 behavior. You have also his data at this pressure. You see where correlations are much stronger. You are on the verge of solidification. And as you can see, he still has some T-square behavior on a more limited region compared to this one. So these are really low temperatures, and the slope has become larger. Okay, so Of course, in 1984, this was analyzed and understood in the language of Fermi liquid and the Landau parameters associated with correlations. Now, let me now tell you how people understand T-square thermal resistivity in helium-3. They do not invoke two reservoirs. All fermions are similar in helium. There is no lattice. There is no place for umklapp. You have just normal scattering, and you have a T-square resistivity. How come? Well, as you know, the diffusivity in kinetic theory of gases is just proportional to the square of velocity. This is the mean velocity of your molecules or your particles. This is their scattering time. This prefactor depends on dimensionality, and this gives you a diffusivity. So this is true for thermal diffusivity. This is true for momentum diffusivity or viscosity. Now, if you take this energy diffusivity and this specific heat, now thermal conductivity, basically the product of these two. Specific heat is linear in temperature. Thermal diffusivity is proportional to T minus 2. You end up by having a thermal conductivity which is proportional to inverse of temperature. And in the language of metal physicists, this is this thermal resistivity, which is T squared. Now, if I look at helium under pressure, this has been documented by Greyval's experiments. As you can see, specific heat is increasing. This is just because, you know, correlation are becoming stronger. This prefactor of thermal T square resistivity, which is kappa T divided by mi, is also increasing because of thing. And you see that actually the theory gives a fair account of this data. This is a theory by Diane Pettig, the Fermi liquid theory, just by taking the Landau parameters and calculating the thermal conductivity. So theory works. Now, let's come back. And this is what was not done before 2020 for reasons that I don't understand. If you put now helium-3 and compare it with this term in metals, basically I am using the same data. This is, you see there is the number in the case of helium-3, and for the other metals, this is basically the slope of WT, which I call B. They match. So helium-3, of course, has a much larger gamma because we are talking about the specific heat of fermions which have the mass of the order of 3 times a proton mass, which itself is 1,800 times larger than the mass of an electron. These guys are heavy fermions, so they have heavy electrons, but of course not as heavy as helium-3. But you can see that the same physics seems to be continuing here. The difference is that for this physics, we don't need umklapp or anything, and it comes from basically Fermi liquid parameters. For this physics, people start with electrical resistivity. They look at the Widman-Franz law, and then they look at the T-square thermal resistivity, which suggests that if we begin on the other way around, the T-square thermal resistivity by itself in these systems is not a surprise because you can analyze it exactly as you did in the case of helium-3. Now, if I go one bit further and I show the variation of this term in helium-3 and in strontium titanite, you can see that again, there is the same tendency. The Fermi energy in strontium titanite is small, but of course is larger than helium-3. You see that the slope is not exactly the same, but you see that the two physics are going to meet again. So this brings us to this idea that what drives T-square resistivity in helium-3 and in metals should be related to each other. And we should have in mind that in the case of helium-3, this Fermi liquid is not replaced by a non-Fermi liquid, it is replaced by a solid. This brings us to the last part of my talk. I would like now to talk about strange metallicity of cuprates. Well, Here's a phase diagram from this review paper by Bernard Keimer and collaborators. You know this phase diagram most probably. This is a subject which has been a source of fascination, debates, controversy since 1980s, and still an unsolving puzzle. What generates this superconducting dome? What I would like to talk about is this part. So there is a Fermi liquid here, and this Fermi liquid is no more here. And suddenly the system becomes a strange metal. Now, I would like to begin by mentioning an old work by my friend Nigel Hussey. So what Nigel and collaborators did was that they showed that actually, if you look at the evolution of resistivity in this system, when you are at 33%, where the system is no more a superconductor, resistivity can be fitted by a T-square term. So this is alpha 2 here. And there is no actually T-linear term. As soon as you become superconductor here, there is a finite T-linear term. The magnitude of T-square term doesn't change that much. So here is the puzzle. During what remains of my time, I would like just to mention it. How can we understand the fact that this metal has a T-square resistivity? It behaves like a Fermi liquid, but as soon as superconductivity emerges, you have very much difficulty, I would say impossibility to fit it with a T-square term. You need to invoke a T-linear term which grows as you decrease the carrier density. Okay, so the reason I'm interested in is that actually we did this experiment before in 2003. At that time, the paper was not accepted in PRL because people could not believe that it is T-square, but it, we measured on 2 different samples, and you can see that there is a purely T-square term when you are out of this superconducting dome. There is no superconductivity down to 10 millikelvin. So this is a heavily overdoped LSU. And at that time, we put it on the Kadowaki-Woods scaling, and you can see that actually it is 5 times higher. But 5 times maybe it's not a big deal. At that time, you can say that it is large, but how large can it be? Now, 20 years after, let's look at this 2003 data. Actually, if you compare LSU with other oxide perovskites, these are all perovskites which are dense, so you can use Kadowaki-Woods scaling, and you see that LSU is here. Kadowaki-Woods scaling actually works very well for systems which belong to the same family. Here, these are perovskite oxides, and you see that this is not the case of this guy. If we use this ratio of T-square resistivity to Fermi energy, all these guys are in the same range. And actually, again, LSO, it's still, you find something which is not completely unrealistic, but it is even higher than these heavy fermion guys. So let me come back to helium-3 and mention one thing. So we know that mass increases when you put pressure, and the Fermi liquid eventually dies because the more pressure you have, the larger is the amplitude of fermion-fermion interactions. Now, here is the question. Why does the Fermi liquid disappear in helium-3? Now, one thing that we can say is that you can define there a kind of dimensionless amplitude of T-square resistivity, in the sense that if you take the scattering times T-square and multiply it by the Boltzmann constant square and divide it by Fermi energy, you find a number which is extremely small. Then here you have a sudden solidification. The system suddenly becomes a solid. This is a number I define here, zeta minus 1, which is basically the scattering time, the fermion-fermion scattering time, times T-square. So you can see that this is a dimensionless number. It has no dimension, and it has its inverse has become very small here. Okay. Why does the Fermi liquid disappear at a given pressure in helium-3? I propose, I speculate that this is because this quantity cannot become arbitrarily large. Zeta cannot become arbitrarily large. The lambda parameters are two particle correlators. They can become large, but they cannot become infinite. There should be some cutoff. Of course, there is no rigorous theory putting this bond. All theoretical treatments I am aware of assume that the lambda parameters diverge at the mode transition, but experimentally this is not the case. Helium-3 is a Fermi liquid, it remains a Fermi liquid, and suddenly at some particular pressure, when these lambda parameters are huge but not infinite, the system ceases to be a Fermi liquid. Now let's come back to cuprates. There is one important gradient about the cuprates, is that the Fermi surface is well known. And so this is the evolution according to Arpes. And I am interested in what happens for the extremely overdoped cuprate. Here you can see that this electron-like, in hole-like Fermi surface becomes an electron-like here. And actually, at 32%, the Fermi surface is very well given by a tight binding model. We can actually, and this is what you expect also according to LDA calculations, if there was no mode transition. You have numbers, all of them fit what the Arpes Fermi surface at this sloping is given. Now, what is particular is that you have a strong modulation of the Fermi velocity. So you see, this is the anisotropy of the Fermi surface, and this is the anisotropy of the Fermi velocity. The interesting fact here is that the anisotropy of the Fermi velocity is much larger than the anisotropy of a Fermi radius. So if you put these numbers and you calculate what is your scattering rate between as a function of temperature, you find that this scattering rate is also extremely anisotropic. And if we look at its angular variation normalized by the Fermi energy, as I did in the case of helium-3, for nodal particles, it becomes extremely small, enough for making the nodal quasi-particles incapable of participating in the Fermi-Dirac distribution. Now, if this happens, then the reason T-square resistivity ceases to be accurately valid below this scattering time is this, because we are in presence of a system in which a subset of carriers are no more part of the Fermi sys. This will, of course, generate a linear term. The reason is very simple, because the reason you have T-square resistivity is that both electrons belong to the same Fermi sea, and you are supposed to employ the Pauli exclusion principle twice. If one type of electrons is classical, then you would expect a T-linear resistivity. This is what happens when degenerate electrons are scattered by classical electrons, or degenerate electrons are scattered by phonons above the Debye temperature. So this is the end of my talk. I would like to begin by just summarizing it in this way, that I think the main message is that there is a deep connection, which was not noticed before, between the amplitude of T-square resistivity in metals and the amplitude of T-square thermal resistivity in helium-3. This, in my opinion, indicates a common origin. This would explain why T-square resistivity persists in metals where no collapse can be conceived. and why the prefactor of T-square resistivity can be guessed knowing the Fermi energy. Finally, the third part of my talk was a speculation, but based on this observation that if you take this dimensionless amplitude of T-square resistivity, it is remarkably large in LSCO, in heavily doped LSCO, and comparable to what was seen in helium-3. If there is a boundary to what can be the size of this dimensionless T-square resistivity, then it is much less surprising that this boundary is met by subset of electrons in the heavily doped cuprate system. So thank you for your attention, and I'm ready to take questions.
Yeah, thank you, Professor Behnia, for this nice, very informative colloquium. Now the floor is open for question. So we have also some audience in the room, Silver Jubilee Hall. So maybe from there also people can ask, and also from the online audience. So maybe the online audience we start first. So please raise your hands. Yes. Yeah, you can ask.
So I can ask the question, right? Only one audience here, it's me.
Yes,
so,
yes.
Mr. Behnia, thanks for the nice talk.
Thank you.
Thanks for the nice talk. I have one general question: that what favors for superconductivity, square or non-Fermi liquid? Fermi liquid or non-Fermi liquid?
Excuse me, I didn't understand the question. Can you repeat it?
In general, for superconductivity. So
Yes.
what favors most, T square or less than, like, non-Fermi liquid?
Sorry, can you repeat the question? What is the question?
The question is, resistivity versus temperature problem, and you mentioned like Fermi liquid behavior, right, for metals, and for even many superconductors, for example, cuprates also shows kind of metallic, like dopes of cuprates are metallic in nature. Am I clear with my voice?
Yeah, your voice is not very clear, but you can just you can speak louder, and go ahead.
I'm using a mic, so I don't know.
Yeah, I think I can repeat the question. I mean, saying that Seti, probably you can correct me if I'm wrong. He is trying to ask that in superconductors, whether these behaviors are like a Fermi liquid or non-Fermi liquid, isn't it?
I mean, it depends on the material, but in general, what favors most? Fermi liquid or non-Fermi liquid?
Yeah, but what is a non-Fermi liquid? I don't. You see, I try to.
Non-Fermi liquid, like it's proportional to T. Let's say, not like T square.
But I showed data when we look very carefully. I am interested in specific questions. So let me just maybe again show, because you see, here is a very specific question. You see, as you can see in this data, this is a set of data. At 17%, your resistivity is almost completely T-linear. Okay?
Yeah.
Almost completely. Here, at 33%, it became T-square. It is perfectly T-square. Okay? Now, look at here. So this is the result of fits. They use different kind of fits. And what they can see is that at 33%, there is no T-linear term. So I will call it a Fermi liquid. Okay? Here, the T-linear term is much larger than the T-square term, and the T-square term maybe is absent. You see, they cannot say. But the most important point in my understanding is here, you can no more talk about a Fermi liquid, because whatever you do have a T-linear term. It is finite. Okay? It is not purely T-square. But here, it is a Fermi liquid. So, the whole point is this. You begin with a Fermi liquid, and at some point you are losing it. I try to address this question, why? Is it an answer to your question?
This is specific to cuprates, but is this, my question is this common for every material or every superconductor? For example,
no, you see, UPT3 is a superconductor, but it is T squared. Strontium ruthenate is a superconductor. You know, I showed, I don't, you know, I don't think it is a good idea to be so general. You see, these two guys are superconductors. UPT3 is a superconductor as is T squared. Strontium ruthenate is a superconductor, it is T squared. Organic superconductors, if you look at the resistivity near the TC, it is also T squared.
Okay, so now coming back to it is not a big issue, like having T squared or linear, it's not a big issue for superconductivity, for having superconductivity.
I didn't catch your point. What was your
superconductivity? So will it be an issue, like T squared or non-T squared, will it be an issue for having a superconductivity? For like, no, I'm not going for like no specific material, but I'm just looking at the problem in general.
So what is the question?
The question is for superconductivity. So like, you know, yeah, anyway, yeah, thanks. I think I'll let you name. Maybe that will be more straightforward. Thanks. Yeah.
Yeah. So
okay. You're welcome.
Yeah. So yeah. So do we have more questions? So please raise your hand for questions. Yeah, I saw one more. Yeah, maybe I can. Yeah. So yeah, Professor Manoranjan Kumar, you can ask your question.
Please go ahead first, and then I'll try.
No, you can start. You can start.
Yeah. So I mean, like, is there any material where this Fermi and non-Fermi liquid both are some sort of like linear combination, or sort of the system behaves both way? And
I just showed LSO. This is the in L and in cuprates in general. You see, let me put it this way: in cuprates, you can get T square resistivity in some regions, and when the sub TC is higher than this is maximum, you don't have T square resistivity. This is you know, you can never fit it with a purely T square term. On the other hand, in high TC cuprates, this is really what I want to underline. This is not maybe when you go at 33%, it is T square. There is no T linear term.
I see. And is there, I mean, the mechanism for the mixing? So in general, these mixing, is there some specific mechanism, or like it can have? Okay.
So let me. Okay, very good. But this is, I'm just speculating. You know that this T linear resistivity has a prefactor which is called Planckian. It is H bar divided by KBT. So you can have this kind of T linear resistivity when, for example, electrons are scattered by phonons above their Debye temperature. Of course, this cannot be the case here because we have T linear resistivity at very low temperature. It is below the Debye temperature, and it is about electron scattering. But the idea is this: if the reason electron phonon scattering gives something which is T linear, and the prefactor is almost H bar over KBT, is because phonons above their Debye temperature are classical objects. Yeah. So if two electrons which are colliding to each other, one of them is classical, you get T linear resistivity, and it will be mixed up with T square resistivity.
Okay.
Here is what I propose as an idea, but of course this is just a speculation.
Okay. Thank you very much.
You are welcome.
Yeah. Atin, you can ask your question.
Yeah. Nice talk, Professor Behnia. So I have a question related to your initial slide on bismuth and graphite. where you showed that the linear region is for bismuth is T square is much higher and graphite is only till 30. I don't remember the actual scale. So is it just related to the Debye temperature, like of these two different systems? Why the scale is different?
This is a good question. Actually, no, I think, well, the Fermi energies are comparable. So normally you see this T-square behavior in any system which is, so normally you should expect to see them almost at the same temperature. In graphite, you see there is a sample question. You see you have C-axis. I think this is some kind of, this is my guess. Graphite being an isotope.
Network issues, I cannot hear it properly. Yeah, sorry.
Do you hear me?
Yeah, some network issues were there.
Yeah, we can hear you.
Okay.
Probably, I think.
Okay, yeah, okay. Good. Okay, maybe in my office here. Okay, yeah. Can you please, continue.
So your point is very good. I think the only reason what sets this region of T-square resistivity is the Fermi energy of a system. So both graphite and bismuth have a Fermi energy of the order of 200 Kelvin. So in bismuth, actually, the T-square resistivity is not perfectly T-square. The exponent is close to 2, but not exactly 2. And in graphite...
Yeah, I saw some deviation. I saw some deviation in bismuth.
Yes, there is some deviation.
Okay, so related to this, so in case of graphene, for example, we generally see a different type of temperature dependence. I guess the temperature dependence is not well understood in graphene.
Yes, but in graphene, if you look there, my former student, Alexandre Javi, who is now in Barcelona, he published a paper in Nature Physics recently. So you can see also a T-square which becomes T-linear. So, I think the story I am saying is actually most probably also relevant to graphene. If you look at the way T-linear becomes T-square there, it's very much reminiscent of cuprates.
So, in principle, you are saying if it is related to the Fermi energy, so if you use a gate voltage to go near to the Dirac point and away from the Dirac point, the behavior will change, right?
No, well, yeah, but you have, it's also dependent on angle. You see, if nobody has seen, so in graphene, pure graphene, single layer graphene, people have not seen T-square, but most probably because people have not looked for it. In twisted bilayer graphene, people have seen T-square. They have attributed to umklapp, because if you have a twisted two-layer graphene, then you have a Brillouin zone, and which is very small, and that small Brillouin zone, in that case, you can conceive T-square resistivity. But you see, I think it is surprising, because if you take the magnitude seen there and put it on our graph, it also matches the Fermi energy.
Yeah.
You see, all of this is something which is going to be revised, because people in graphene have not compared their T-square resistivity with what is seen, for example, in heavy fermions or in the Strontium Titanite.
Yeah, that's an interesting, the scaling thing. Yeah, this is very interesting. Yeah. Thank you, Professor Behnia.
You are welcome.
Nitesh, you're mute.
Yeah, sorry, I was on mute. So you were telling about momentum conserving electron-electron scattering. So are there any other mechanism for which this momentum is conserved in scattering? For example, people also talk about phonon drag in the case of hydrodynamic systems. So can you comment on that?
Well, you see, okay, I will put it in this way. Two electrons which collide conserve momentum then there are collisions between electrons which don't conserve momentum. These are Umklapp collisions. Okay. When you discuss about hydrodynamics, you are interested in these normal non-Umklapp electron-electron collisions. Now, recently, it has been, both theoretically and experimentally argued that some of these normal collisions between electrons can be driven by exchange of phonons. Phonon electron collisions, but with phonons, which is of course true. And part of the interpretation, so the idea is that part of the reason in some cases you have very frequent electron-electron scattering is because of this presence of phonons. But this is another issue on top of the idea of Umklapp. If you look at most these dilute systems like antimony, the Fermi surface is so small that again you cannot conceive Umklapp, but still you have T-square resistivity, which suggests that you have both dissipative T-square resistivity and normal T-square resistivity. But I don't want to enter that. This is by itself also a very interesting issue.
Yeah, also related to this Kadowaki wood. So when I was going through these earlier papers where this modified Kadowaki woods, this nature physics paper. So in that it was a discussion that you should not consider this rule for semi-metallic systems, for example, dilute systems where the correlation is not very high. So now you have shown that all these, for example, zirconium, tellurium 5, zirconium, silicon, sulfur also in between those two straight lines. So you think that all these semi-metallic systems can be put in this Kadowaki wood?
Well, I this is fact. You see, I begin with, again, I make an observation. I make an observation is that if you take the Fermi energy, of course, if you have a complicated system, you can have several Fermi energies, but you can have an average Fermi energy. Then the magnitude of the T-square resistivity is not surprising. And again, if you go back to helium, there the situation is much less surprising. And if you compare helium with these metals, it looks like there should be a very common origin. I make observations, and from observations you can make some deductions about what's going on. So yes, I think there is a kind of universal scaling.
And does the dimensionality of the system also enters in this Kadowaki woods? For example, any quasi one-dimensional or two-dimensional or three-dimensional?
It changes a little. Of course, it changes because you have details which are different. And this is not a universal. It's not like it's not a constant. It's about the order of magnitude. So dimensionality doesn't change the order of magnitude. We are talking about something of the order of something, which is like something between 1 and 10. So when you have different dimensionalities, you can have pi over 3 or pi 2 over 5, these kind of prefactors which are different.
Okay. Yeah. Thank you very much. So do we have more questions? I think if not the case, then we should thank the speaker again. So thank you Professor Kamran Behnia. It was very nice experience for us. You gave a very nice overview, very fundamental talk, very useful for our students also. We would like to see you in person here in Kolkata. Maybe we'll.
Yeah, that will be good. Yeah.
Yes, I hope that one day.
Because you are the expert in this thermal transport, and we also try to start something on thermal transport. So we'll have some interaction, then will be very useful for us to go ahead in this field.
With pleasure. Hopefully, when things become normal, I hope to visit you. Okay. Goodbye.
Yeah. Thank you.
Bye-bye.
Bye.